Hello and welcome back to the course on statistics. Okay, so today we're talking about a student's t-distribution. A very interesting topic. It may be a bit scary sometimes when you hear it because there's so many things to keep in mind. There's the Z statistics, which we've already talked about. There's the central limit theorem. There's the p-values, the Z test, which is the hypothesis test, and the proportions. Already so much, and that's why another type of distribution might be a bit off-putting. But at the same time, it's actually pretty simple. Without going into the complex maths, you will see that it is straightforward what is going on, and it's very easy to apply in practice given the knowledge we already have. So let's dive straight into it. Here we have a gentleman called William Seeley, I hope I'm pronouncing that right, Gosset. He was a statistician who worked for the Guinness Brewery in Ireland. And he actually published the t-distribution under a pseudonym student. And there's lots of speculation about it. Like I read on Wikipedia that maybe the Guinness Brewery didn't want their competitors to know what they're using the t-distribution for. And what he was using it for was he was interested in analyzing chemical properties of samples with very small sizes, as few as 3 elements in a sample. Can you imagine that? Like we were working with samples with like 150 or 100 or 50 or at least 50 or like larger samples. So sometimes you might have a sample with 1,000 if you're doing a big poll or something. And he was trying to analyze, make inferences about populations from samples as small as 3 elements. And so that's where the t-distribution is like it has its place. It has its little niche in the world of statistics. It deals with situations where your sample size is rather small. So this is what the t-distribution looks like. Look familiar? It's very similar to the normal distribution. In fact, it's just like a modification of the normal distribution. The formula is there on the right. We're not going to go through that. There's like an extra function in there. There's the other thing we will talk about is the degrees of freedom. So this t-distribution, it just has a new parameter that which we're going to have to keep in mind, degrees of freedom. And degrees of freedom is very simple. Here it's written out 1 degree of freedom, 2 degrees, 5, or infinite degrees of freedom. Degrees of freedom is basically the the size of your sample minus 1. That's all it is. So your t-distribution, it has heavier tails. It's very similar to the normal distribution. In fact, over here, this black one, the one where degrees of freedom is infinity, so your sample size is infinity, or is huge, that is a normal distribution. So as nu gets larger and larger and larger, this whole thing, it converges to a normal distribution. So that's just something to keep in mind. So it is a modification of the normal distribution, and all it does is, let's look at this orange one, for instance, or this purple one. You can see that it has heavier tails. And it is useful because these heavier tails suggest that this distribution that you're creating it can actually produce values further away from your mean. So it facilitates outliers in an easier fashion than the normal distribution. So it's not as strict as a normal distribution. And that's kind of like your penalty or the price you pay for having a small sample size. So if you still want to apply all of the same logic that we've been applying so far, you can, by using the t-distribution instead of the normal distribution, but you will pay the price of it having higher tails. Remember what we do with the tail? The tail helps us reject the null hypothesis. So we say, if we're at 5%, for instance, in the normal distribution, if we're at 5%, we can reject the null hypothesis. Well, in the t-distribution, the tail is thicker, meaning your 5%, it'll be further down on the tail. So if for a normal distribution, the 5% sits over here, so if that's minus, let's say that's minus 2 standard deviations, then remember your 5% sits somewhere over here, before the minus 2 standard deviations. Well, for a t-distribution with few degrees of freedom, like 1, your 5% will sit further away. So it's harder to reject the null hypothesis when you're using the t-distribution. That makes total sense because you have a smaller sample size. So if it was as easy to reject the null hypothesis as in the case of a normal distribution, then you might get a lot of false positives. You might get a lot of situations where you reject the null hypothesis, but in reality, you shouldn't have rejected a null hypothesis simply because your sample size was small and you had a sampling, you were lucky that you were able to reject the null hypothesis. That's what the t-distribution combats. the situation where, because your sample size is small, you might reject a null hypothesis in cases where you shouldn't have. That's all it does, and therefore it has these wide, thicker tails. And as you can see, as your degrees of freedom increases, meaning your sample size increases, your tails get narrower and narrower and narrower, and they approach and converge to a normal distribution as degrees of freedom gets to infinity. In fact, it doesn't have to get to infinity. As long as degrees of freedom is around 30, your t distribution is pretty much identical to a normal distribution. So think of it as 30 is at infinity. So yeah, that's what 30 is. So it has heavier tails. It describes a sample. So that's also important to remember, that the t distribution doesn't really describe your population. It describes a sample, but that's kind of like a technicality, or it's a more of a it's quite an important underlying concept, but it's not really going to affect us as much, because we're going to come up the way we're going to approach it. We're just going to have a standard process that we're going to be going through, and it will already take into account the fact that it describes a sample. So, but it's just probably good for you to know that it describes a sample rather than the distribution originally, which we've been working with so far. Normal distribution, we use it as a descriptor of the actual population. But this doesn't stop us from making inferences. You'll see we'll be able to make inferences using the t distribution. And another thing is, the larger the sample, the closer it is to normal distribution. And we've discussed that already. So there we go. Your degrees of freedom increases, goes up to the top. So let's have a look at that in action. This is all from Wikipedia. So just look at blue is your normal distribution, ideal. So that's when you have a large sample size is large. Yeah, so no, blue is just a normal distribution. Red is the t distribution. Then what happens is we increase, so 1 degree of freedom, meaning the sample size is equal to 2, sample size is equal to 3, 2 degrees of freedom. What's happening is the red is the new t distribution, green is the old t distribution. So all of the old t distributions are going to be in green. Blue is still that normal distribution, which as you can see, the red distribution is coming closer. So you go from here to here to here to here to here to here. So as you can see, it's getting closer and closer and closer. So 1, 2, 3, 5, 10, 30. So 30 degrees of freedom. Well, that's the sample size of 31, but we're just gonna, like you can see, it's still not exactly on the blue, but it's very close. So our cutoff point is going to be 30. And that's where these rules come from, that we use a t distribution or a t-test. It's also called a t-test. You've probably heard that. When the population standard deviation is unknown and the sample size is small, less than 30. So very important that both of these conditions are met. So the way this is interesting how it works. The t distribution, as you can see here, allows you to calculate. Remember, we'd normally have your sampling standard deviation over here, but in this case we have the sample standard deviation divided by the square root of degrees of freedom. So basically, it allows you to operate in environments where you do not know the standard deviation of the population. But at the same time, so that is kind of like the normal thing for the t distribution. Population standard deviation is unknown. But at the same time, as we saw previously, when your sample size is 30 or greater, your t-test, your t distribution becomes identical to a normal distribution. So the question is, what's the point of using a t distribution in a case where, even though you don't know the standard deviation of your population, it is identical to a normal distribution? So in that case, you still use a normal distribution, and that's it. Pretty straightforward. And you can approximate your standard deviation from your sample standard deviation, and that's all you need to do. So basically, as soon as you hit that 30 mark, what happens is your t distribution becomes becomes your normal distribution, and whichever approach you take, t distribution or normal distribution, you're going to be doing the same thing. So we just use a t distribution only in cases when we don't know the population standard deviation and the sample size is small and is less than 30. Now make sure to check out these videos on the right or the full course in the description to continue your learning, and I look forward to seeing you there.